it's not a clone of Earth. But for the first time, planet hunters think they have evidence of a planet about Earth's size that could have liquid water in orbit around another star. Kepler-186f, the outermost world of a 5-planet system, orbits about 3 times closer to its star than Earth is to the Sun. But that star, Kepler-186, is an M-dwarf. It's much cooler than our bright Sun. So, scientists of the SETI Institute at NASA Ames Research Center are confident the new world is in the so-called habitable zone of that star. M-dwarfs live very long lives, plenty of time for possible life forms to develop and evolve. M-dwarfs also tend to flare more than our Sun, but Kepler-186f is thought to be at a safe distance, and the enhanced radiation might possibly speed the mutation rate of organisms, driving nature's evolutionary tinkering there. This planet, discovered using the transit method by the highly successful Kepler mission, is only about 10% larger in a rocky world, like Venus, Earth, and Mars in our own solar system, which hold atmospheres made of gases released by their own volcanoes and water collected from impacting comets. Planets larger than about 1.5 times Earth's diameter begin to draw atmospheres made of hydrogen and helium, like our Neptune and Uranus. And they keep on puffing up, like our Saturn and Jupiter, and even growing much, much larger into what scientists call super-Jupiters. Gas giants are not conducive to life on their surfaces, if they even have solid surfaces. No one knows at this point what the surface of Kepler-186 is really like. If there is water, it could be frozen, because the planet is pretty far out in the star's habitable zone. But being larger than Earth, it might hold a thicker atmosphere, which could keep the temperature up and the water liquid. As for the possibility of life on Kepler-186, that may have to wait for a future generation of telescopes. The planet is about 490 light-years away. We'd likely need a powerful space-based instrument to detect oxygen, ozone, or methane in its atmosphere. Seeing those gases in abundance would likely be the products of biology, life as we know it. Of course, there is a small, but not unrealistic chance that intelligent life could have evolved there, and an even smaller, but still valid possibility that they are, or were, transmitting radio signals now detectable by our technology. Specifically, the SETI Institute's Allen Telescope Array, which has, in fact, begun making wide frequency range sweeps of that part of the sky. For Space.com, I'm Dave Brody. And if you have a question about all this, tweet me at DavidSkyBrody.
Earth's energy balance will enable you to understand radiative equilibrium. You will also be able to recognize that the temperature of Earth depends on the amount of solar energy that it absorbs. The temperature of Earth depends largely on the total radiation received from the Sun. The Earth reflects about 30% of the solar energy radiation reaching it and absorbs the remaining 70%. The absorbed solar radiation heats up the Earth. While the Earth continually absorbs solar radiation, it will not simply continue to heat up. In response to this heating, the Earth emits long-wave radiation into space. The emission of long-wave radiation cools the Earth. As the Earth cools, it emits less radiation to space, but because it is still continually absorbing solar radiation, it still heats up. As it heats up, and so it cools. This dynamic physical process of absorption and emission and resultant heating and cooling creates what is known as a state of equilibrium. The term equilibrium describes a stable condition where all of the influencing factors are in balance and so cancel each other out. Because of this equilibrium, the temperature of the Earth has been relatively constant over time. For scientists, this balance between the amount of solar radiation absorbed and the amount of long-wave radiation emitted by the Earth is known as radiative equilibrium. Radiative equilibrium tells us that the long-wave radiation emitted by the Earth will equal the amount of solar radiation that is absorbed by the Earth. In fact, we can determine the temperature of the Earth by knowing the amount of long-wave radiation it emits. If one of the components of the Earth's energy balance changes the amount of long-wave radiation the Earth emits, the temperature of the Earth will also change, and the Earth will arrive at a new radiative equilibrium. For example, if the amount of solar radiation absorbed were to suddenly increase, the amount of long-wave radiation emitted would also increase. The temperature of the Earth would then increase, but a new radiative equilibrium would be reached, so the Earth would not continue to become hotter. In summary, the Earth's radiative equilibrium describes the balance between the incoming shortwave and the outgoing long-wave radiation. The temperature of the Earth can be determined by the amount of outgoing long-wave radiation, which is equal to the amount of incoming solar radiation absorbed by the Earth.